Okay guys, this is section 5.1. In this section, our goal here is to be able to simplify expressions involving powers. So, we have the properties of the exponents that you should probably have seen back in Algebra 1. Our first property here with the exponents are the product of powers. Okay, and this says if you have the same base, in this case we say a or whatever base we have, variable, or it could be a number. If they are the same and they're being multiplied together, all we need to do is add their exponents together. So for example here, I have off to the left, the bases are 5s, and since they're the same and they're being multiplied together, all I need to do is add their exponents. So 3 plus -1 does give me 2, and I can actually evaluate that because that's just a number squared, and 5 squared is 25. The next property we have is the power of a power. This says if you have a base raised to an exponent, but it's raised again to another exponent, the whole thing, all we need to do is multiply those exponents together. So for example, if I have 3 to the third power, and that whole thing's raised to the second power, all I need to do is multiply the exponents. So 3 times 2, well that's 6. And we can evaluate that. 3 to the 6th power is 729. The third product here, or third property here, we have the power of a product. So that means is if I have two different kind of bases being raised to the same exponent, all I need to do is split them apart and raise them to that same exponent. So for example, I have two different bases over here, 2 and 3, and I'm going to distribute that exponent of 4 to both of those bases on the inside. Okay, so it becomes 2 to the 4th power times 3 to the 4th power. And 2 to the 4th is 16, and 3 to the 4th power is 81, and when I multiply those, that is 1,296. That fourth property, we have the negative exponent. So if we have negative exponents, what we're going to do is flip it to the bottom, the whole thing, that base raised to the exponent, and then we're going to make it a positive number, or a positive exponent. Okay, and just leave 1 or anything positive to begin with on the top. So for example here, if I have 7 raised to the negative power of 2, I'm going to flip that whole thing over, so the base of 7 raised to that exponent of 2, and it's going to be under 1. Okay, so all my positive stuff stays up top. And 7 squared, I can evaluate that. That's just 49, or 1/49. The next to the last property here, we have the quotient of powers, and that says, well, if we have the same base and we're dividing them, all we need to do is take the exponents and subtract them. And I kind of like to always remind myself I need to subtract the exponents because of that division bar there, and it kind of looks like a minus sign. Okay, so if they have the same base, that's when you're subtracting them if you're dividing. Okay, so if I have a basis of 6 here in this example, I need to do -3 minus -6. That's kind of tricky here because I got to change that. Okay, that double negative. So it's saying -3 plus 6. Well, that's just 3, and 6 to the third power, we know that's just 216. Then our last property, we have the power of a quotient. And that says if we have a fraction raised to a exponent of some sort or power, all I need to do is distribute that power to both the numerator and denominator. Okay, then, for example here, I have 4/7 raised to the 7th power. I'm going to distribute that exponent of 7 to both the 4 and the 7. Okay, so that's actually a typo. That should be a 2 here, not a 7. So distributing the 2 to the 4th power and 2 to the 7. Okay, that becomes 4 squared over 7 squared, which is just 16/49. Okay, so 16/49. So there's all of our properties for our exponents. So let's try to apply some of these. Okay, so in this one, I'm trying to evaluate -4 times 2 to the 5th power, which is all raised to the 2nd power. Okay, so to begin with, what I am going to do is distribute that outer exponent of 2 to the 4 and to the 2 to the 5th power. That came from our power of a product rule or property, okay? So that's going to become negative 4 to the 2nd power, and yes, I'm going to put that in parentheses because it is a negative, times 2 to the 5th power to the 2nd power, okay? Well, I know negative 4 squared, that's just negative 4 times negative 4, that's 16. And 2 to the 5th power to the 2nd power, if I multiply my exponents here, okay, coming from the power of a power rule, that gives me 2 to the 10th power. But 16 times 2 to the 10th power is 16,384. So here's our answer when evaluating that whole expression all the way down. The next example, we're going to do the same thing. So if I evaluate this one, well, my power of a quotient property says, okay, I could take my outside power and distribute it to my numerator and my denominator. Okay, so that becomes 11, and then 5 times negative 1 is negative 5. And in the bottom, 11 to the 8th power, okay, but I got to multiply that 8 to the negative 1, becomes 8, but negative, okay? Then, since these are both negative exponents, I need to flip them, right? So if I flip 11 to the negative 5 over, remember your exponent becomes positive 5. And if I flip the 11 to the negative 8th power, it flips to the top and becomes positive. Okay? Now if I look here, well, I have the same base. That's 11 and 11. Since they have the same base, I just need to take my exponents and subtract them. Okay? Remember that minus sign there when we divide. So that becomes 11, and 8 minus 5 is 3. And 11 to the 3rd power is 1,331. So here's my answer evaluated all the way down from that expression. Alright, so in other math classes, any science classes, you might have already worked with scientific notation. Again, scientific notation is just a representation of a number. It could be a really, really big number or a really, really small number, okay, of the form C, which is a constant, times 10 to some power exponent, okay? And it's always going to be that base of 10, where 1 and 10 is somewhere in between for that constant. So it can either be 1 or it could be less than 10. And n, or that power, is an integer, okay? So if your n is positive, though, it is a big number, so like in the thousands, millions, okay? But if your exponent or power n is negative, a negative integer, then you know it's going to be a small number. So like 0.0034, where it's small, not big, in the thousands or millions. Okay, so to help practice with scientific notation, this word problem says a swarm of locusts may contain as many as 85 million locusts per square kilometer and cover an area of 1,200 square kilometers. About how many locusts are in such a swarm? So first what we want to do is probably put 85 million into scientific notation. Okay, so 85 million, if we write that out, that has 6 zeros in it. Okay, and if I want to put that in scientific notation, what I need to do is put the decimal point on the end and move it to where it's in between the first two non-zero digits. So I count 1, 2, 3, 4, 5, 6, 7. So my decimal point's in between the 8 and the 5, the first two non-zero digits, times 10, and my exponent 7, because that's how many places I moved to put it there. So here is that number in scientific notation. Now I need to put the area of square kilometers in scientific notation, so 1,200. square kilometers. Okay? And if I do that, again, since it's a big number, I'm going to put it on the end, my decimal point, and move it 1, 2, 3. So 1.2 times 10 to the third. In between the 1 and the 2 because of the first two non-zero digits I got. Okay? So I got 8.5 times 10 to the 7th and 1.2 times 10 to the third. And what I'm going to do is I'm going to multiply these two. Because, again, our question is about how many locusts are in such a swarm. I need to multiply those. Okay? So what I'm going to do is multiply the regular numbers together. Okay? So 8.5 times 1.2, that is 10.2. And then I'm going to look at my bases with the exponents. Okay? So they have the same base, so I'm going to leave it as 10. And when they're being multiplied together, we're going to use that product of powers rule. Since they have the same base and they're being multiplied together, all I need to do is add their exponents. So 7 plus 3, that gives me 10. Okay? But I'm not quite done because I have to move this decimal point over one more because that's now in between the first two non-zero digits. Okay? So this is 1.02. And since I moved it one more place to the left, I'm going to add one more to my exponent. So 1.02 times 10 to the 11th. Okay, and if we put that back as a regular number, that is 102 and 9 zeros. Okay, so that's a pretty big amount of locusts in that area of just 1,200 square kilometers. Okay, so not only can we evaluate using exponents and do scientific notation with them, we can also just simplify normal expressions with variables x, y, z. Okay, so a simplified expression contains only positive exponents. Again, if we have any negative exponents, we have to use our properties to get rid of them too. So for example, I have all the same bases here, okay? They're just b's. So what I could do, since they're being multiplied together, again, that product of powers property or rule that we had in the beginning says if they have the same base, all I need to do is add the exponents. So negative 4 plus 6 plus 7, okay? But when I evaluate that all the way down, negative 4 plus 6 plus 7, that is 9. So b to the 9th power, and that is it. That is simplified all the way down. And our last example here, okay, I'm going to simplify this one. Even though it looks scary, remember all of your properties that we talked about at the beginning, okay? Well, just right off the bat, I see this power of outside 2, right? What I could do with that is distribute it to the inside. Our power of a product rule told us that. Okay, so if I simplify that, that's x, and I'm multiplying here, so negative 3 times 2 is negative 6. And then if I look at the y, 3 times 2 is 6, all over x to the 5th, y to the 6th. And now we're dividing here, but remember, when we have that fraction bar, it's really like subtraction, okay? So we're going to line up our like bases. So the x's with the x's and the y's with the y's. And we're going to subtract. So x, and we're going to take negative 6 minus 5. Well, that is negative 11. And then if I look at the y's, y to the 0th power, because 6 minus 6 is 0. Okay? And then y to the 0th power, that is always going to be 1. If you put 1 to the 0th power, 100 to the 0th power, 1,000 to the 0th power, that's always going to be 1. So this is like saying x to the negative 11 times 1, which is still x to the negative 11. But remember, negative exponents get flipped over too, okay? So if I flip x to the negative 11 over, remember the exponent becomes positive, and since I don't have anything else that's positive, it's just going to be a 1 in my numerator, and that's going to be it. So here's my expression all the way simplified down for that final example there.